All right, the code in Lab 6, there's two different files, okay? They're like 90% similar. Just to go, there's lab06a and then lab06b .py. In the code, I mean, the big piece that's missing is really this function brightness extractor 2, most of which you will have already written. Okay, so this is really going to be something where you go back and look at homework 5, then see what you did there, right? And then move most of it over. You're going to have to change some numbers, right? Because that was written for a different type of photoresistor. We're giving you a new one here, the one that you're actually building with. All right, so you're going to have to be writing this code, and then you're going to maybe need, well, not maybe, you will need to change a little bit of stuff right here, okay? And that basic, and the thing you're going to have to change boils down to the fact that whenever we read a channel, an analog input, so actually while we're on that topic, so in this lab we're reading in analog signals, right, through the MCP 6008, sorry, the MCP 3008 chip. What that returns back is, if you remember from homework 4 and 5-ish, this is talked about, digital systems, when they read analog signals, they don't inherently think of those signals as volts, right? So if we remember, right, if you have, let's say, this is a plot of voltage on a signal over time, right, and you have your some signal and it's going up and down or whatever, okay, even though we as humans know that if we were to read it right here, it's actually, you know, this is 2.7 volts. If a digital system, right, a computer, some sort of microcontroller or something were to read it, it doesn't see this as 2.7. It sees it as whatever the bin number is of the analog to digital converter. And remember, these systems, they basically have very, very fine gradations about how they describe voltage levels. And then these are numbered, you know, so these are numbered based off of like the number of bits you use to describe the voltage. So the MCP chip which you're using, that's a 10-bit ADC, okay? Which means it describes its voltage range, its input range, 0 to 3.3 volts using 2 to the 10 values, okay? So 0 to 3.3 uses 2 to the 10 values, which really means, and what's 2 to the 10? So that's going to be, what, 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128, 2 to the 8 is going to be 256, 2 to the 9 is 512, 2 to the 10 is 1024. And then, or what you actually, your maximum value for 10 bits would be actually 2 to the 10 minus 1. So you're going to be describing 0 to 3.3 volts using 0, 0 to 1, 1. Okay, this is equal to 1023 in binary, and this is equal to 0 in binary. And so that's what read channel, this function right here, returns back. Now don't worry too much about like what this is actually saying. What this is really doing is getting at a bunch of bits from some registers and then returning them. But whenever read channel returns back a value, it is not in volts, it is in bins, and your job in this code will be to, one, change it to volts using what we just described, okay, and then two, use your brightness extractor 2 to produce a illumination, which we then just report using that speaking guy. Going back to the top real quick again, just to go over some things, doing some imports up here. Note that log and exponent are imported for you down here. We do the voice command. I'm making a note right here that depending on, I believe there's a version issue between Python 2 and Python 3, but if you wanted to have like whispers and do voice modifications, I believe you need to do string formatting rather than raw formatting whenever you're dropping the command argument in. These just set up the pins. This sets up SPI, which is a communication protocol we use to talk with the MCP 3008 chip. Read channel is the function which we're giving to you to read that chip. Resistance extractor is provided for you, but you also actually wrote that in another exercise, just keep in mind. Yeah, and then you have your main loop down here, and it's just basically reading an input. You have to convert it to volts, print it just for, you know, the sake of printing so we can see it, generate an illumination, and then report that illumination verbally. Wait a tenth of a second and restart. Now there's also another file we're working with, and it's basically the same thing. Actually, let's just kill this one. Okay, 2, 1, there we go. So again, the top of this looks basically the same. The difference here, though, is what I want you to do is, as shown in the video too, by the way, I want to have the photoresistor right here. Okay, and it's got little leads coming down, and they're going to go back to your chip, and then it's even got that zigzaggy thing in it. Okay, and I want an LED shining on it. All right, and this LED can be any color you want. I don't care. Well, what I want this system to do is I want it to maintain a certain level of brightness in this region right here, okay? And so I want it to do that by going over here, and that illumination, I want it to be contained in this variable desired illumination, okay? And the idea behind this code is now, again, brightness extractor, you just copy this from Labo 6A, but we're going to take a reading, you're going to have to convert it, all right? We're going to figure out the illumination, and then what you need to do is I need you to adjust the brightness of that LED based off of what the current illumination is, okay? So you're going to need to figure out what the illumination is, compare it to the desired illumination, and either increase or decrease the brightness of the LED. Now, if you in the video for Lab 5, where we talk about the piezo unit with the tone generator, we talked about pulse width modulation. PWM, which is pulse width modulation. Okay, and the idea behind pulse width modulation was, if you remember from that video, the digital outputs on the Raspberry Pi, all they can do is be 0 volts or 3.3 volts. But by making them go, instead of, always on or always off, if you have them go on and off quickly at differing ratios, so where you're maybe, if we were to zoom in here, if you're on 50% of the time and then off 50% of the time, okay, and then you do this, hundreds of times per second, what you can do is, if you average it, it looks like, it's a little bit dimmer, actually. So instead of it being always on or always off, it's 50% on. And our eyes are too slow to actually detect the on-off nature of it, and so we end up sort of blurring it together, time averaging it with our eyes. So you can basically feed a PWM into an LED and then make its brightness go up or down just by turning it on or off at different ratios. So instead of being 50-50, if you are, let's say, on 10% of the time and off 90% of the time, this is just 10, what that does is then the LED over time, on average, looks dimmer to us. Okay, so what we can do is by changing this PWM value, and you can do that either via the, so we could do PWM, I believe it's change duty cycle. You might want to double check that. Change duty cycle of LED, or just by doing PWM of start LED, what you can do is on the fly change the duty cycle we are providing to the LED, and as a result, you can change how bright it looks. Okay, and so your job is to figure out how much do we change it by every time, based off of are we brighter or not. If we're, if there's too much brightness, we want to back down the LED. If it's not enough, we want to bump the LED up. Okay, and the idea behind this is how you could have some sort of, for example, like those garden lights, which never really seem to work, but everyone buys them anyways, that like turn on at night. Okay, they basically bring the LED on whenever it's dark outside. Or an inverse of this would actually be screen auto brightness, right? Whenever it gets dark, your iPad or your phone or something will actually dim its screen because it realizes it doesn't need to compete with room brightness as much anymore. So that's actually the opposite of what we're doing, but through a simple minus to plus sort of situation, you could actually implement something like that. So that's what you're doing in both of these labs. If you have any questions, post on the forum.